Okay, so we are going to be now looking at something that's hypothesis testing with using the normal distribution. But actually what we're doing here is we're hypothesis testing on the sample mean. Now, before I even start really looking at this, okay, this is something that is used an awful lot in the real world, okay? If you imagine that you were the owner of a huge factory and, I don't know, you were making like boxes of chocolates or something, or you were making a bar of chocolate, and you wanted to check that the machine that was making the chocolate bar was actually doing as it was told, and it was making the chocolate bar with the correct number of grams in it. Let's say it was 100 grams. Now, you wouldn't test every single chocolate bar that comes out and measure its weights, okay? You would take a sample from the number of chocolate bars from your factory, and you would weigh them, you would do tests on them to see if you were actually complying to that law of 100 grams for your bar of chocolate. And what this is about taking a study, this is about studying taking samples from a huge population of chocolate bars and taking the mean of those chocolate bars and trying to decide if there is enough evidence, if your mean is different to the overall mean, to say, hang on a second, these chocolate bars in this factory have actually gone down, the average of chocolate in each bar has actually decreased. Or has my machine broken a bit and my machine is putting too much chocolate in and actually we're underselling the chocolate. We're actually giving people more chocolate than they need. Now, you might do that as a factory owner, but you also might do that if you were someone who goes around to check that people are complying to the law. Because if you're going to be selling a bar of chocolate and it says it's 100 grams on the back of it, and you are one of the people who works for this agency that will check these companies are doing this, if they go around and they take a sample of 100 chocolate bars from your factory and they perform this hypothesis test on it and it fails the hypothesis test, that company then becomes liable because they are potentially trying to like cut a few corners here and there, save some costs, and actually lie to the consumer. So there's actual laws around this, and the law is all based around this maths that we've got here, okay? So this is the kind of basis for what we're doing. The idea is that you've got a whole population of things. We're taking a sample from that whole population, and we're trying to figure out if that mean is different from the overall population. So we're going to have a look at it with some example of, not to do with chocolate bars, but just really some random numbers here. And I've said, not random numbers, but I've said imagine that we have 10 children, one of each age between 0 and 9. This is our population because it's the whole thing that we're looking at for these 10 children. And I've said this, there is a known population mean of mu equals 4.5. So that might be on the chocolate bar what you say the chocolate is going to be in the bar. It's not exactly going to be 100 grams every time, but on average it will be. So suppose that we took a sample of 4 children. This is a bit like in that example I was just saying. You as the factory owner said, I'll take 10 chocolate bars off the line. Well, in my first sample that I took randomly a child with 1, 3, 7 and 8, which gave me a sample mean, which is an X with a bar above the top of it, not mu. It gave me a sample mean of 4.75. So in this first one, the average is 4.75, and it's actually pretty close to the true population mean of mu, but naturally it is going to vary as we take different samples. It might just be that you happen to have taken the top 4 students, the top 4 children, or it might be a mixture of them. If I took another random sample, this time I've taken 6, 2, 0 and 9, I got a slightly different average. I got 4.25. So for this different sample, we might obtain a different sample mean. And what we were doing in this table over here is I was starting to tally the kinds of sample means that would turn up if I took these 4 random people from the overall thing and to try and think what would happen. So I've said what would happen if we took lots and lots and lots of different samples of 4 and found the mean of each. How would these means be distributed? Well, this graph has been done by taking 1,000 random samples from these 10 pieces of data that we've got at the top here, and it creates this kind of distribution that we have here. This kind of distribution that we have down here looks like, what does it look like? Looks like the normal distribution. Okay, it does look like the normal distribution because we've got this kind of pattern that we've got here like this. So it means that when you take a sample many, many, many times, we should expect it to be distributed like a normal distribution. And that kind of makes sense. If you just kind of pause for a second and think to yourself, okay, you've got these 10 numbers here, and if you're going to take 4 of them, and you're going to keep doing that, a lot of the time you would expect it to be near the population mean of 4.5. But sometimes you're going to get unlucky, I should say, in inverted commas, and you might actually get the 6, the 7, the 8, and the 9, and you might get one of these extreme values down here. And we're trying to figure out now, when should we be starting to think, actually, the mean is different to the overall population? So we're just going to talk a little bit more about what this looks like on the next slide here. So X bar, this is now capital X bar, is our distribution across different sample means as we consider different samples and different sample sizes. So I've got these 2 different things that I've got here. This one is taking a mean of a sample of 4 units. So when you take 4 units, in other words, we just took 4 children, we've got this kind of spread out shape that we've got over here. Now, I've just noticed I've got these numbers not matching up each other in this second one. I think this is probably more likely that we've taken 6 units and 6 children from here. So this time we've taken slightly more children into the sample. I realised before when it said 10, it wouldn't make sense, because if you took 10 units out of 10 things, you're going to get the exact same mean every time. What do you think looks different between these 2 distributions when you took more in the sample?
The area is more concentrated in the second one.
Yeah, the area is more concentrated in the second one. And if we're going to try and use some mathematical terms, some statistical terms to describe this, what could you describe about the way that this is distributed versus this one, trying to use some statistical terminology?
The standard deviation is further up with the first one?
Good. The standard deviation in this first one is larger than in this second one. The standard deviation in this one at the top means that the data is more varied, okay? Which makes sense. If you're only going to take 4 out of the 10 things, it makes sense that you might get 4 of the most extreme ones, or you might get 4 of the least extreme ones. So you're probably going to have these extra tails at either end. If you're taking a larger group, maybe of 6 or 7 children out of the 10, yeah, it means it's probably going to stick closer to what the true mean is, which is 4.5, okay? So let's just quickly read through the answers to these questions, and then we're going to talk about this bit in the purple box at the bottom. So what type of distribution is X bar? Well, it looks like it is approximately normally distributed. We've already talked about that one. On average, what sample mean do we see? In other words, what is the mean of all of these means that we have taken? And it looks like that the sample mean will vary around the population mean, but on average, we think that the mean of the sample means is the population mean. In other words, when you take lots and lots of samples of these chocolate bars from the factory, on average, we expect their averages to be the average.
Nice.
Okay? But that's what you would expect. Okay? If you kept doing this over and over again, you should think that that would happen. Now, this is a bit where Muzuki just answered my question. I've said, is the variance of X bar, i.e. how spread out the sample means there are, the same as that of the variance of the population of the children? Well, no, it's not going to be that, because on the left, we can clearly see that the sample means are dependent on the sample size. So the variance of the sample means are dependent on the sample size. If the sample size is small, like this one at the top, then they are likely to vary quite a bit. In other words, the variance is going to be large. If the sample size becomes slightly larger, we expect the different X bar to be closer to the population mean of mu. So we expect the means to be closer to the center. In other words, we expect the variance to be smaller. Okay? Yes?
So we want the variance and standard deviation to be smaller.
Yes, so ideally you would like the variance to be smaller if you were talking about this in a practical sense. I wouldn't go into your chocolate factory and say, I'm going to test your chocolate bars by taking a random sample of 3 chocolate bars out of the 100,000 that you're making. They're probably going to start thinking, okay, well, they would perform some math to think, what is the most reasonable size that we could take? They're not going to take a sample of, how many did I say, 100,000? They're not going to take 100,000 chocolate bars, and they're not going to take 3 chocolate bars. They're going to have to take something where mathematically they can be pretty sure to a high confidence level, to a high statistical significance, that you're either like, that your factory is working well or your factory is not working well. So this is the last bit that we need to know here. I've said for a random sample of size n taken from a random variable x, the sample mean, x bar, is normally distributed. So x bar is normally distributed. We expect it to have the same mean, but its variance is different. The variance is sigma squared over n. What do you think n represents? Oh yeah, sorry, it says n, sample size of n. So if you just think what's happening there, if you take a huge sample, what happens to the variance? It becomes smaller, like this, like it's starting to vary less and gets just closer to the mean. And if you imagine that you took loads and loads and loads and loads and loads of samples, this would basically become 0, and it would be normally distributed as basically just a spike at the mean, which would make sense. If the sample that you take is quite big, or bigger, your variance relatively will be bigger. Sorry, if your sample that you take is small, you're right. If the sample is small, the variance will be bigger and it will look like this one that we've got at the top here.
And that's what we don't want.
And that's what we don't want. Although in the questions we're going to do, we won't be in control of like how many n's there are, but just the more n, the larger the n is, the more like reliable your hypothesis test will sort of be thinking about.
Maybe question, like comment on the comment on the effectiveness of this. With the process.
They could say something like, I haven't seen them do this in any of the questions, but it could be like state an improvement to this model, and it could be like increase the number of samples to increase the size of the sample. That might be something that you could think about. Okay, so one thing I just wanted to point out before we move on here is we're talking about the sample means being normally distributed. The original population that we had here was just the population of those children. Were their ages normally distributed? No, their ages were just this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's not a normal distribution. So we're not using this for things that are necessarily normally distributed. We could be doing it to any random variable, and when we take those things, the means of the samples are the things that are normally distributed. So what we're going to do is we're going to kind of dive in straight away to thinking about doing a hypothesis test, right? And we can pretend that this hypothesis test is about a product, and we're going to do a couple of these, and then we're going to do one that has got like a worded kind of context that goes with this. So a random sample of size n is taken from a population having a normal distribution with mean mu and variance sigma squared. Test the hypothesis at the given significance level. So I've got two of them that we're going to do here, okay? I've got this hypothesis test and I've got this separate one down here. My first one says that my null hypothesis is that the population mean is 15. Maybe we're talking about a small chocolate bar here, okay? And I think, I've been eating these chocolate bars recently, and I've been thinking, I swear these are like just a little bit lighter. I've been weighing them at home. Something seems a bit weird here. I actually think that the average has changed, and I think it is now less than 15 grams. What I then did is I took a sample of 30 different chocolate bars, and I was told that the standard deviation was 1.5. The standard deviation of the whole population was 1.5. And when I did these 30 chocolate bars, I actually found out that the average was 14.5. And that made me think, okay, well, I think that the average must be less than 15, because I've weighed these 30 chocolate bars and I found out that the average was 14.5. So we now know we're going to assume that H0 is true, which means that I think Y bar, I think that my sample means will be distributed normally, and I think that they were going to, I'm guessing, I'm going to presume that they have got a mean of 15, and the next bit we have to be careful with, I know that the standard deviation is 1.5, so I'm going to put 1.5 squared, and I'm going to divide it by how many I took in the sample, which is 30. Do you need a booklet maybe?
Basically, we think that for the given us less.
So I have just said, okay, you know what? I'm going to pretend that this chocolate company is telling me the truth and that the chocolate bars are 15 grams, and I'm going to actually find out what are the chances that it is true. What are the chances that I actually do get an average of 14.5 or less? It's like the same way with binomial hypothesis testing. We're looking at things being more extreme. I want to know the probability that my chocolate bar is 14.5 grams or even smaller than that, because that would also make me think that the probability has changed. So I'm now going to find out what is the probability that y bar is less than or equal to 14.5. Do not confuse this with continuity corrections, okay? That continuity corrections is only for binomial stuff. This is nothing to do with continuity corrections anymore, okay? So I'm going to go back to my camera and I'm going to try and type this in. So let me just quickly grab this. Okay, so we're going to go to normal distribution and the probability, not probability distribution, the cumulative one. And we wanted it to be less than 14.5, right? So my lower is going to be minus whoosh. My upper is 14.5. Now, this is a bit we need to be really careful of. The standard deviation that we've got here, this is the variance. So the variance is 1.5 squared over 30. So what would the standard deviation be? Root that, yeah. And if you root the top and you root the bottom, you get 1.5 over root 30. So I'm going to be typing into my calculator 1.5 over root 30. So I've got 1.5 divided by root 30. And they said that the average was 15. So we get that the probability is 0.0339. So, what does this tell me about my chocolate bar that I took the sample of?
It's really unlikely to be 15.
It's really unlikely, but I was testing it at the 1.1% significance level.
That's right.
So actually, this is bigger than 0.01. So although from these 30 chocolate bars, there was only a 3% chance that my chocolate bars had an average of 14.5, that's still bigger than my 1% significance level. So there is not enough evidence. There is not enough evidence to reject H0. Now, my question doesn't have a context, but you know if it did have a context, if you don't write a context comment, you don't get the last mark. So if it was about the chocolate bars, I would say the mean of the chocolate bars, there's no reason to think that the mean of the chocolate bars is less than 15 grams, okay? We should still think that it is 15 grams. I just got a 30 chocolate bars that on average were a bit less, okay? So let's have a look at this one. You can already probably tell me what's going to be different about this. It's a two-tailed test, so I've got the 5% significance level here. I'm going to be having to look at it as a 2.5% level because it's two-tailed. So I'm still going to write out my null hypothesis, is that this time I think that the mean is 120. My null hypothesis is I think that the average is not 120. I'm going to get over this chocolate bar analogy soon, okay? But the average is 120, and I've taken a sample of 25 things, and I found that the average was 124. What am I thinking? Even though I've said I don't think that the average is 120, if I took a sample and I got 124 grams, yeah, I think it's in the upper tail. I actually really think that the mean is bigger than 120. But I've said here that it's not 120. So when I think about doing the probability, I'm going to be saying, what's the probability that it's 124 or even bigger? Because I'm already saying here it's bigger than the mean. So I'm like, I want to know what's the probability it's 124 or bigger. Okay, so we assume, as we always do, we're going to assume that H0 is true. In other words, that means that I think, because we're talking about x here, I think that x bar is normally distributed with a mean of 120 and a variance of 12 squared over 25. So I get 12 squared over 25. Now you might like to sort of say to yourself, okay, well if this is the variance, then the standard deviation will be the square root of this. This one looks like an easy one to do a square root. I've just got 12 over 5, okay? Then I'm going to find out what is the probability that my x bar is bigger than 124. The reason I'm concerned about it being bigger is because the average is 120. I've got 124, so I want to know, whoa, what's the probability it was 124 or even bigger? It's always more extreme in the direction that we've got, okay? So I'm going to come back to my calculator now. So I'm going to say, I want to know that it is bigger than 124, so I'll do my upper as my whoosh. And we said that the standard deviation was 12 over 5, and the average was 120. And we get that the probability is 0.0478. 0.0478. Now, if you thought this was a one-tailed test, what would you have said?
It's great, less than 5%.
You would have said it's less than 5%, and you would have been like, reject the null hypothesis. I don't actually think that the mean is 120. But we're all smart enough to know that we had to half it here. So we're actually then going to say that this is greater than 0.025. So there is not enough evidence to reject H naughts. In other words, in the context, we would say there is no reason to believe that the mean is different to 120. Yes, Hamza?
See how there's a little y bar and a big y bar and a little y bar.
Yeah. So, oh yeah, so the little y bar, this is the sample mean of my 30 things. And the capital Y bar is the distribution of all of the sample means. So capital Y bar is the distribution of all the sample means. So the little one is like, it's just one of them, and the capital one is the distribution of all of them that ever could possibly exist, okay? We're only taking one sample, but we know that all of the samples do have that normal distribution. Yes?
So if we didn't do a two-test test and it was one-tailed,
Yep.
would we accept it?
If it was a one-tailed test, let's pretend that that mu was greater than 120, then, so it's a 5% one, we would say that it's less than 5%, so we would accept the alternative hypothesis, or we would reject the null hypothesis, which makes me think that actually if I took these 25 things and I measured that they had an average of 24, it would make me think that that chocolate bar in that factory, something about the machine is breaking and just on average is putting too much chocolate in, and we're losing money as a company.
So when we get a value which is within the percentage,
Yeah.
then we accept the H1.
Yes, it's kind of like the same thing that we talked about with binomial, where the probability that you took a sample of 25 things and you got an average of 24 is 4%, which is quite rare to happen, but it's not rare enough to happen. Okay? So if it's just, the significance level is just kind of semi-randomly chosen, we're saying 5% is a significant thing for it to be quite random that needs some more investigation to see that would happen.
So,
Yeah.
the calculator gave me something else.
Have I typed something in wrong? I possibly have done.
It gave me one.
So you've got the lower is 124. That's why.
Ah.
So it's 124 and that makes sense. If you're saying what's the probability that if you took a random sample of something that has an average of 120, you would expect everything to be bigger than 24, wouldn't you? Which is why your calculator gave you 1. Okay, so we've done them 2 like this. You're going to do some practice for them that are kind of no context at all, because I want you to do lots of these for practice. We're going to do 1 now with some context, and then you're going to do some practice. Then we will finish the topic off by doing some of them with critical regions, and then we're done. Yeah?
Can you explain why you divide the variance squared variance that put it over the
why it's over the value of n. So the deep reason of why it's divided by n, I can't go into the deep reason because I actually don't know the deep reason why it's divided by n. But the intuition of why is because if you are taking more in your sample, then the variance decreases. You see how this graph is kind of shrinking towards the middle. So if you think about making n bigger, then the overall thing here gets smaller. In other words, the normal distribution sort of shrinks to the middle. But the actual proof of why it's divided by n, I haven't actually looked into that, so I wouldn't be able to explain that. Okay? So we're just going to do one more question here. Now we're going to talk about fruit juice in cartons. And this is genuinely how factories and producers will actually look at these kind of things. So it says a certain company sells fruit juice in cartons. The amount of juice in a carton has a normal distribution with a standard deviation of 3 millilitres. The company claims that the mean amount of juice per carton is 60 millilitres. A trading inspector has received complaints that the company is overstating the mean amount of juice per carton and wishes to investigate this complaint. The trading inspector takes a random sample of 16 cartons and finds that the mean amount of juice per carton is 59.1. Oh my gosh. They might be cheating. We need to find out. Okay, so you're going to be the factory superheroes. You're going to work out what happens using the 5%. The factory superheroes. You're going to go in and see, is this company like trying to destroy consumer rights here? Okay, this could be your future job. You could be this trading inspector if you wanted to be. So using a 5% level of significance and stating your hypotheses clearly, test whether or not there is evidence to uphold this complaint. So, null hypothesis, what? Mu is 60. Alternative, mu is smaller than 60. Other things that we know about here, and I always like to write these down as well, we've taken a sample of, the standard deviation is? No, the standard deviation for the whole thing was 3, because we'll change this in a second. And we took a sample of fruit juice in a carton, so we'll just call it Y bar, maybe, was 59.1. So we are going to, and we could say that the significance level, I don't know if you've seen alpha for the significance level, is 5%, and it's going to be one-tailed. Sometimes if you just write all that information down at the beginning like we had on the previous question, it just makes it a bit easier. So we're going to assume that H0 is true, which means that we think that our distribution, Y, of the sample means will be normally distributed with a mean of 60, and this time we think the standard deviation is going to be 3 squared over 16. So somewhere else on your page, you might like to say to yourself, okay, well that means that the standard deviation is 3 over root 16, which is just 3 over 4, okay? We're now going to say, what is the probability that if I took these measurements, that I got 59.1 or more or less? Or less. I want to know that the probability that Y bar is less than 59.1. So I'm going to 59.1. Oh, I always do that wrong. Negative whoosh. 59.1. The standard deviation was 3 over 4, right? And the average was 60. And you get 0.115. Did I type that in right? Everyone else get 0.115. And 0.115 is bigger than 0.05. So not enough evidence to reject H0. There is no evidence to support the claim that the amount of juice is less than 60 millilitres. Hamza.
See how you have to define the test statistics for binomial?
Yes. There's actually not a mark for it, but you're right. We should say like, let Y bar be the mean of the sample, means of the samples, So you could say that, but there's not actually marks that are reserved for that kind of thing. So then all I've put in that note is don't confuse X and X bar. X is the distribution over amount of drinks in each individual carton. X bar is the distribution over the sample means. So the possible sample means we see as we take a sample of 16 cartons. X might not be normally distributed, but X bar will be. That's what we talked about at the beginning where we had the kids different ages and we said they're not normally distributed, but their sample means will be. This one happens to be that if we called our juice Y, Y is actually normally distributed because they tell you in this question that the amount of juice has a normal distribution. So Y happens to be normally distributed, but the sample means will always be normally distributed because of those graphs that we saw earlier on. So we're going to do a few questions. We're going to do questions 1, 3, 5, and 8 from exercise 3G, okay?